Alright, ladies and gentlemen, welcome back. Today what we're going to be focusing on is trying to determine if a complex number is going to be a solution to a particular equation or expression. Well, let me rephrase. If I'm saying it's a solution, I'm really not going to use an expression, but uh, we're going to be taking kind of an old skill but applying it to a new type of number, in this case complex numbers. Think back to problems maybe such as this, where you had seen something like said x squared plus 3 is equal to 7, where let's say x was equal to 2, and you want to say is 2 a solution. Even going back to maybe pre-algebra, where you got an answer to a problem and the instructions that was on your assignment or that the teacher gave you said something along the lines of you have to check your answer and make sure it works. It's kind of the same thing. We're going to take a number and substitute it into a problem to check to see if it is a solution or not. So in this example that I'm giving you, we would substitute the 2 in. So I would say 2 squared plus 3 is equal to 7. Well, 2 squared is 4. And so 4 and 3 is 7. So in this case, we would say yes, it is a solution. Whereas after I evaluated it, if it didn't balance on both sides of the equal sign, we'd say no, it's not going to be a solution. Now, because we are going to be working with complex numbers, these two particular rules that we established in our previous lesson may be beneficial to you if we are trying to substitute a complex number into, say, an x squared term like that, where we would have to FOIL it out. So if you remember the two rules, it can save you a little bit of math as far as the foiling is concerned. Otherwise, you just FOIL it like normal. So looking here, here's our first example, similar to what I just showed you a second ago. X squared plus 25 is equal to 0, where x is equal to negative 5. Is that a solution to the equation? This one is really easy to try and solve, or to check with substitution. We're going to substitute the negative 5 in for x. So if I say negative 5 squared plus 25 equals 0, let's see what we wind up with. Well, negative 5 squared is negative 5 times negative 5. So that is going to give me a positive 25 plus another 25 here to be equal to 0. Well, on the left side, 25 and 25 is 50. And 50 does not equal 0. So in this case, we would say no, negative 5 is not a solution. Now let's work at this, let's take a look at this just a little bit backwards. Again, thinking back to maybe pre-algebra days or early algebra days when your teacher said, once you know your solution to your problem, substitute it back into the equation to see does it balance. Okay, well let's take a look at just the equation itself. Let's see how would we solve it normally. So how would I solve x squared plus 25, 25, getting ahead of myself here, to be equal to 0. If we were going to solve for x, the normal thing that we would do, we would say subtract 25 here, and on the right side, these are opposites, that's negative 25. So now I have x squared to be equal to negative 25. At this point, take the square root of both sides. The square root of x squared is just x. The square root of negative 25, well, now that we've been talking about complex numbers, we know really that could produce either a positive or a negative 5i. And I want to write the radical sign again here for some reason. So those are really the solutions to the problem, not a negative 5, but a positive or a negative 5i. And I want to note one thing right here real quick. Positive 5i and negative 5i, those are conjugate pairs. So this is kind of leading us into the idea that if I have one imaginary number or one complex number, as a solution to a problem, then its conjugate pair must also be a solution to a problem, and that's going to be coming up in later units as well. So since we're talking about solutions to complex numbers being solutions to problems now, I just figured I'd start throwing that little tidbit out there for you. So anytime I have a complex number as a solution to a problem, its conjugate pair will also be a solution. So let's take a look at this one. Now here we're substituting a complex number, a negative 8i, into the problem. So let's take a look and see how this one's going to go. If I substitute negative 8i in for x squared plus 64, let's see how this one's going to work out now instead. Now we're squaring the 8 and the I that's inside of the parentheses. So negative 8 squared, negative 8 times negative 8 is a positive 64, and I to the second power will give me I squared as well, plus 64. Now again, from previous lessons, we've established that I squared is really just the number negative 1, so we'll substitute negative 1 in for I squared, and 64 times negative 1 gives me negative 64 here, plus 64 here, to be equal to 0. And negative 64 and a positive 64 are opposites, so that looks like it works out to be a good solution. Now again, I just want to look at it from the other perspective. What if I asked you to solve the problem? Instead of saying that maybe 8 is a solution or negative 8i is a solution, how would it look if I just asked you to solve this particular problem? Well, if I said x squared plus 64 is equal to 0, and I tried solving for x, move the 64 over by subtraction to the right side, and I get x squared to be equal to negative 64. And undo the square with the square root, and that'll give me x to be equal to, and again, the nice thing is that now we have an idea of what complex numbers are doing and how we work with them. So the 64 could be a positive or a negative 8, and the negative of the square root gives me I. So not only does negative 8i produce a solution, but a positive 8i would also produce a solution. But long answer short is that, is negative I or negative 8i a solution to the problem? Yes, it is. Yes, negative 8i is a solution. Okay. Now here is where we might want to need to know one of those special rules depending on what we wind up with in the parentheses. So let's take a look at it first. Let's substitute the expression that we have for x, which is 2 minus 6i. So if I substitute 2 minus 6i in for x, I'm just replacing the x itself with that. So that's because the x becomes 2 minus 6i, but I still have this negative 2 that I have to keep inside of the parentheses. And we're going to square it, and that's equal to negative 36. Now inside of the parentheses, you can see right away that the positive 2 on the left and the negative 2 on the right, those are opposites and cancel each other out. So now I'm just left with negative 6i in parentheses squared being equal to negative 36. Okay, well, let's see what we get. Negative 6 squared will be a positive 36. I squared is I squared equals negative 36. And of course, I squared is negative 1. So that gives us negative 36 to be equal to negative 36, which appears to check out as a solution. Okay. This one here would be not really complicated to try and solve, as you know, for the other two examples where I tried working it from the problem itself to see what the solutions would be. But we're going to hold off on this one here. But we could probably work it out. Let's just go ahead and do it. Since I'm talking about it and I've done it for the other two, let's just go ahead and see what would this be as if I just said what would be the solution of x. So if I say x minus 2 squared is equal to negative 36, Well, I can just go ahead and start off by taking the square root of the whole thing. So on the left side, something where I square it and take the square root at the same time, those cancel each other out, and I'm going to be just left with x minus 2. And the square root of 36 will give me either a positive or a negative 6i. And from there, we can move the 2 over through addition, and I will get x to be equal to 2 plus or minus 6i. And 2 minus 6i was one of the two possible solutions. But again, it's just a good indication to explain to us that solutions that have, or problems that have imaginary or complex solutions, their solutions come in conjugate pairs. Now this one here is going to get a little bit ugly as far as the math is concerned, depending on how comfortable you are with the rules that we established in the previous video and what we just saw at the beginning of this one, where we have the sum or the difference of something of a conjugate number squared. Because that's exactly what we're doing, is we're going to take this expression 3 minus 4i and substitute it into the anywhere I have an x. So if I substitute into the first x where it's x squared, I'm going to say 3 minus 4i, and then I have to square that, plus 12, and then I'm going to substitute 3 minus 4i again, plus 25 to be equal to 0. Okay, so let's go ahead and expand this part out so those of us that need to see it can see it. So that'll be 3 minus 4i times 3 minus 4i plus, and let's go ahead and distribute here. The 12 multiplied to the 3 will give me 36. The 12 distributed to the negative 4i will give me a minus 48i. And oops, I don't need that parenthesis. Let me kill that guy out right there. And plus the 25 equals 0. Okay, so now here, depending on if you remember the rule or not, we can either use the rule or we can FOIL it. Okay, for the purposes of demonstration, I think I'm going to just go ahead and FOIL it. But if you want to use the rule and just skip to after I FOILed it, please just kind of go ahead. The 3 times 3 gives me 9. The 3 and the negative 4i give me negative 12i. The negative 4 and the 3 give me another negative 12i. Negative 4i times negative 4i is going to give me a positive 16i squared, and then plus 36 minus 48i plus 25 equals 0. And you can see here we have some like terms, so let's go ahead and combine those. 9 minus 24i, the 16, the I squared changes to a negative 1, and just carry down the rest of the stuff here, plus 36 minus 48i plus 25 equals 0. And now let's just continue with our operations here. Let's change the negative 16, or the 16 times negative 1. Let's go ahead and change that to a negative 16. So 24i minus 16 plus 36 minus 48i plus 25. The reason I'm not combining any like terms in the meantime is simply because I want everything in its simplified form before I combine like terms. You're welcome to start combining, say, like the 9, the 36, and the 25 as like terms if you want to. Personally, I just prefer to simplify everything before I combine like terms, just to make sure I don't miss anything. So here I have a 9 minus 16 plus 36 plus 25, which ultimately works out to be 54, and then a negative 24i minus a 48i, which gives me a negative 72i, all to be equal to 0. And so there's no more like terms that we can combine. So in this case, we would say, unfortunately, no, 3 minus 4i isn't a solution to the problem. Now in this case, the problem itself that we have is a quadratic function x squared plus 12x plus 25, which we could try factoring, which unfortunately this one doesn't factor, and the only way that we could solve it would be to use a quadratic formula, which I can show you if you're very interested, but I don't believe it's necessary. Unfortunately, this is, I know in the other examples I've kind of shown you like, well, how would you solve it from the problem perspective rather than checking to see if the solution itself works, but I think bringing in the quadratic formula at this point is a little unnecessary, but trust me, and if you want me to show you rather than simply taking my word for it, I'll happily show you why it works. But last thing that we're going to talk about here is simply determining, well, what if I have an imaginary number whose exponent is greater than, say, 2? Because we've talked about this. We've talked about I being equal to the square root of negative 1, and that I squared is equal to a positive, I'm sorry, to just a negative 1. But what if I had something with an exponent larger than a 1 or a 2? Well, it works out pretty well. If anything that has an exponent of a 3 has a solution that is negative 1i, and anything that has an exponent of 4 would have a solution of a positive 1. And the explanation mathematically is kind of here on this screen for you. An easier way of remembering it is really this part right here. If I divide the exponent, whatever it is, by 4, if I get a remainder of 1, then that means it would simplify down ultimately to just be I. If it has a remainder of 2, the solution would be negative 1. If the remainder is 3, the solution is negative I. And if there is no remainder, then the solution would simply be a 1. Or that's what it would simplify to. Okay, so let's take a look here at these last examples. So all I'm really kind of concerned with is what is that exponent number? In this case, 33. And what we were shown to do in the instructions is to divide that number by 4 and really just look and see what the remainder is. Well, 33, 4 will go into 33 8 times to give me a product of 32. So here I have a remainder of 1. Because the remainder is 1, we would say I to the 33 power is equivalent to just I, 1I, like just like that. And so 72, if I divide that by 4, okay, well 4 goes into 72 18 times with no remainder. So that means I to the 72nd power is really just 1. That's what it would simplify down to equal. And I think you kind of get the hang of what we're doing here. So 11 divided by 4. In this case, 4 goes into 11 only 2 times evenly, which gives us a remainder of 3. So I to the 11th power, because the remainder is 3, would simplify to be negative I. And finally, the 122, if I look at that exponent, divide it by 4, well here 4 goes into 12 3 times, bring down the 2, and 4 doesn't go into 2 at all, so that's 0, but work that through, and we wind up with a remainder of 2, which kind of makes sense since I showed you 3 other problems where the only remainders that we concern about are 0, 1, 2, or 3, and the only one I haven't shown you is the 2 yet. So here, I to the 122nd power really just simplifies to be negative 1 because the remainder was a 2. So that was your presentation there on determining solutions of complex numbers. I know we did just a little bit more. Most people don't think about this last part as determining a solution, but it doesn't really go well with any of the other parts, so we just put it in here at the end. But again, guys, hope you're all taking good notes, and if you have any questions, make sure you come see me for some assistance, and see you in class soon.